Hello everyone, my name is Elijah Proctor, and today we're going to talk about the probability of winning the lottery based off a given scenario. So we have 5 different tests that we're going to go over the Python code for. So the first one asks whether or not the probability of winning the lottery is discrete or continuous, and then calculating the probability of winning the grand prize based on this scenario. And so in this scenario, the probability of winning is discrete, and this is because the outcome is contingent upon a countable set of events rather than continuous outcomes. And so how are we computing the probability of the grand prize? Well, first we have this calc factorial function, which takes in a number and returns basically the factorial value. And then we're going to use that inside of our binomial coefficient function, which takes n and k, or a and b in this case, and it's going to calculate the factorial a divided by factorial b times factorial a minus b. And so we're going to use this binomial coefficient inside this win probability function. And so we have our total balls, which is 51. And how many balls are going to be selected is 6. We're going to pass this into our binomial coefficient, where 51 is n and 6 is going to be k, and this will return our possible outcomes. And the win probability is just going to be 1 divided by the possible outcomes. And so we're going to return that, call the function, store the return value into this winning probability variable, and then just display the results. And as you can see, the probability of winning the grand prize is extremely small. And then for our next task, we're going to calculate the probability of Alexandra winning the grand prize where she buys 1 ticket every 24 hours of every 365 days per year for 80 years of her life, where every ticket costs $5. So we're going to use 3 of the functions from above from the first task, and we're going to add this new win probability at least once function, which takes in the number of tickets and returns the probability of her winning at least once based on how many tickets that she had purchased. So we're going to first compute the single ticket probability, which is the win probability, and then we're going to calculate the probability of not winning a single time, which is 1 minus the single probability, or single ticket probability, and the probability of not winning at all, which is the probability of not winning a single time to the power of the number of tickets that were purchased. And then we're going to return 1 minus the probability of not winning at all, which is our final computation. And then this is a very simple function just to determine how much was spent based on how many tickets there are and how much the tickets cost. We have these 4 constants based on the task question provided above. First, we're going to calculate how many tickets Alexandra purchased over her lifetime, or over 80 years, which is number of tickets, 1 times 365 times 80, which is about 30,000. And then the probability of Alexandra winning at least once, which is the win probability at least once function called with the lifetime tickets passed in as an argument. And then we have our total expenditures, which is just the number of lifetime tickets times the price of the ticket, which is $5. We're going to display the results, and then we're going to visualize the results using some plotting. So first, we have our printed results, which shows that Alexandra's probability of winning the lottery was 0.16%. She had bought 29,200 tickets, and the total amount of money she spent over 80 years is 146,000. So here, this first plot shows the chances of her winning at least once based on how many tickets that she had purchased. And so basically every 10,000 tickets she purchased increased her odds of winning by 0.06%. And the total spending of lottery tickets over her 80-year lifetime, so basically every 10 years or so she was spending about little less than $20,000 on lottery tickets. For the Amir and Friends task, we had utilized the first three functions from task 1, or all the functions from task 1. We have this find minimum trials function, which finds the minimum number of friends who must buy lottery tickets. And here we pass in epsilon as an argument. And so we first use our win probability function, and then we use that here. We first calculate the log of 1 minus epsilon divided by the log of 1 minus the win probability. And then we return the minimum trials that's computed from this calculation. Here we have our epsilon values defined by the task above, and we're going to loop through each value in this array, and we're going to find the minimum trials for each value of epsilon and store it inside this min trials values array. And then we're going to loop, and we're going to display the results for each value of epsilon, and then we're going to display the results on a plot as well. And so as you can see, as the value of epsilon increases, the minimum trials required for different values increases as well. And then for the fourth task, Amir and friends increasing their win probability, we're going to be utilizing the same functions as before, and we have 2 or 3 new functions. One is just for generating the combos. I probably could have used a math library, but decided to generate it myself. And so this is just recursively finding the combinations for a given array with the selected values. So we're going to use that inside this distribute unique tickets function, which passes in, you pass in the number of friends. We have our lists array, which is an array of 1 through 52. And so here we're going to generate the combinations based on this array, and then also 6 values that can be selected. And then we're going to randomly select the numFriends unique combinations from all possible combinations. So just randomly grab them here, store them inside the selected combinations array, and return it. Then we have our compute probability with multiple tickets function, which takes in the ticket per friend and also the number of friends. First we have our win probability calculation, and then 1 minus the win probability stored in our prob not winning single ticket variable, and then we're going to calculate the probability of not winning all tickets, which is this variable to the power of the tickets per friend times the number of friends. And then we're going to return 1 minus the probability of not winning all tickets, which gives us the probability of winning with multiple tickets. So here we have our value for epsilon, which is 0.5, and the number of friends. And so we just pass in the find the minimum trials, so we know how many friends we need for this. We're going to create unique tickets for every single friend. So we're going to have we're going to use that distribute unique tickets function for this, and then we're going to output the unique how many unique tickets just for verification purposes, and then we're going to calculate the overall win probability, which is 1 minus the win probability to the power of the number of friends times the length of the unique tickets. And then we're going to display those results, and then we're also going to generate a plot that visualizes the win probability for different tickets counts per friend. So here we have our number of tickets, number of unique tickets, which is over 12 million, and then our probability of winning increased from 0.5 to 1. So it's a pretty good increase using this distribution or distribution of unique tickets function. And here we have our plot for visualization purposes. And so the final task is the consolation prize task. And so we have 2 functions from the first task, calculate factorial and the binomial coefficient. And we're going to use that for our consolation prize probability. We have our total combinations where with the binomial coefficient, where 51 is n and 6 is k. The number of ways to choose three correct numbers is the binomial coefficient with 6 and 3 passed in, and then the number of ways to choose the remaining three numbers from the 45 non-matching numbers. We have the binomial coefficient of 45 and 3. The number of favorable outcomes is equal to this correct combinations times the remaining combinations, and then we're going to return the probability of winning the consolation prize, which is just the favorable outcomes divided by the total combinations that exist. Then we have our calculate expected value, which takes in the prize amount, and the probability is going to be equal to the consolation prize probability, and we're going to return the probability times what our prize amount is, which gives us our expected value. So in our little scenario, we're going to say the prize amount is $1 million, and the probability is the consolation prize probability, and our expected value is basically our prize amount times the consolation prize probability. So we're going to display the results. We have data visualization plots here as well. One for the likelihood of securing the consolation reward, one for the anticipated value of consolation reward as a function of reward amount. So here below you can see the probability of winning the consolation prize is 1.5%, which is a big significance compared to what we found out in task 1, and the expected value of the consolation prize is $15,758.38 for a prize of $1 million. So we have our plots down here below, and for the last part of the question, introducing the consolation prize should attract more individuals to join the lottery because of these factors, and I think people are more inclined to engage in games when they perceive they have a reasonable chance of winning something significant, and I think this can result in rise in ticket sales, as including a consolation reward increases the appeal of the lottery and improves the overall gaming performance. And so it's logical and to anticipate that this approach would substantially enhance sales and participation. Thank you.